Hello, everyone. I'm excited today to walk you through a powerful and perhaps very little known application of retrieval augmented generation, especially in the fields where context is very of high importance. We are going to explore how RAG solves critical issues in data scarcity and compliance. First, we will start with a foundation introduction to RAG and synthetic data, and then we will dive deep into how these concepts come together to create solutions. Okay. So let me start with a simple question. What would you do if someone asked you a question and you didn't know the answer? And the condition is that you're not allowed to look at the internet or ask a colleague. So many of us in this situation would simply say, I don't know. And yes, that is one way to handle uncertainty. Unfortunately, LLMs often handle uncertainty poorly, and their reactions typically fall into a few problematic buckets. They might respond with, as an AI language model, I cannot answer this question. Or, as of October 2022, my training data does not include this information. So these are failures of knowledge or recency. But then there is the third, arguably most dangerous failure, which is that they could lie confidently. They tend to invent things that don't exist. These are what we call hallucinations. Hallucinations are defined as LLMs generating plausible but ultimately incorrect data points. And this behavior poses serious risks. So maybe you can tell me, which one do you think is worse? The model admitting its limitation or the model inventing a reality that is simply not there? We have seen many real-world examples illustrating the danger of hallucinations. For instance, there were highly publicized cases where lawyers were citing fake cases made up by ChatGPT. Now, things like these, they translate directly into serious consequences for the business, ranging from like poor customer service to severe legal consequences. So when LLMs generate inaccurate or non-compliant information, it leads to low trust in automation due to these compliance issues. So here the business problem is very clear. We need reliable, verifiable, and context-aware data generation. This is precisely where RAG steps in as the solution. So now we can think of RAG as the context provider. It functions like giving an LLM an open book exam. Instead of relying on its internal frozen training data, RAG retrieves relevant information, the open book, and uses that specific text as background before generating an output. Now, since we have gained like a basic understanding of RAG, let's see what synthetic data generation is. Synthetic data is artificially generated data that mimics real-world information and is created using AI. This synthetic data can be used for training, fine-tuning, and evaluating smaller domain-specific models. Critically, it can help mitigate the privacy, the bias concerns by reducing the need to use personally identifiable information. Now, synthetic data is a great solution, but it doesn't come without challenges. While it is useful, generating high-quality, relevant data isn't easy. Without careful constraints, we run into the same LLM issues we just discussed. Some challenges include hallucinations, missing domain knowledge and constraints, and overgeneralization, where prompts alone produce repetitive and shallow datasets. So now this brings us to a specific business problem and use case: synthetic profile generation for medical research, especially on a contraceptive drug trial. So the problem in medical trials, especially for tasks like protocol validation, which means testing if certain people are eligible for a drug trial, or creating evaluation data sets, the data must be very rigorously compliant. And we also need privacy-safe mock data to enable dashboards and QA systems without leaking actual patient data. Now, if we try to generate profiles for a contraceptive drug trial without RAG, we might see simple repetitive data. Perhaps like this table. Page 24, not pregnant, routine check, eligible. The synthetic profiles fail to simulate real-world scenarios, such as pregnancy-related dropout, which is crucial for testing the compliance system. This is where RAG comes to the rescue. Instead of generating data based purely on general training, RAG first retrieves relevant domain-specific context, for example, specific ICMR guidelines, clinical trial PDFs, policies, or protocols. The LLM then uses this retrieved text as background knowledge to generate the synthetic samples. The result with RAG, synthetic data is factual, context compliant, and traceable, making it enterprise ready. Now look at the difference when RAG incorporates the ICMR guidelines. ICMR, by the way, is the Indian Council of Medical Research, which lays guidelines for drug trials like these. Now, if you see if the subject is 28 and pregnant, the eligibility status is not eligible. And the required follow-up action is withdrawn and follow-up. So once a patient enters a drug trial, which is a contraceptive drug, and they start using it, but they get pregnant in between. So when we have generated the synthetic data without including the ICMR guidelines, you don't see that being incorporated in this data. But once we've used RAG, you can see that the data is more relevant to the information and also to the Indian context. So the RAG enhanced data accurately reflects the constraints and specific protocol details, providing crucial diversity for trial simulation. So this is one of the examples where RAG can really help with creating context-aware synthetic data. Now, before we go further, I want to give a brief conceptual overview of what RAG is, and then we will go through the code and see all this in action. So, how does this powerful RAG mechanism actually work? So, the process mainly involves 6 steps. The first one is chunking, where we break large documents into smaller, manageable passages or segments. This affects how complete the context is. And then we convert these chunks into dense vectors using an embedding model. Think of this more like translating the text into a numerical language that the computer understands. The third step is to store these embeddings. Once the text chunks are converted and they are into their vector representations, which are embeddings, they are stored in a vector database such as Pinecone, Chroma, FAISS, or VWeight. This is a persistent knowledge index. Now, when a user, in our case, the synthetic data generator prompt, it submits a query, the query is also converted into the same vector embedding space using the same embedding model. We then search the vector database for semantically similar chunks, which have higher cosine similarity to the given query. This means finding the pieces of the document whose vectors are closest to the query's vector. We retrieve the top K documents which are most relevant to the prompt. Finally, we feed those retrieved chunks along with the original query to the generative model to produce the final grounded output. So now for our use case, this output is the factual compliant synthetic profile. So this is the whole RAG process. We will see it in more detail with examples in the coming slides. And RAG, again, is just more than a chatbot enhancement. It is a critical compliance tool that provides the context needed to transform generic AI output into enterprise-ready, factual, and traceable dataset. By pairing the retrieval capabilities of RAG with the flexibility of synthetic data generation, we can address data privacy and shortage concerns while simultaneously overcoming the critical challenges like hallucinations and compliance failure. Now that we have seen this process on the whole, let's dive deeper into each step. So the first step is chunking, which is basically dividing a long text, like let's say 100+ page PDF, which the ICMR guidelines document is more than 100 pages, into smaller context-rich segments. Like for example, each chapter can be a chunk. 3 to 4 chapters with the same topic can be a chunk. So there are different ways of chunking, which is recursive character text split or semantic chunking. Semantic chunking in the sense where you chunk based on the meaning of the paragraphs, or a sentence or paragraphs based chunking. So it basically is a very important step, and it affects how complete the context is. And again, based on the completeness of this context, the performance of RAG will also be decided. So this is a very crucial step. And once we have these chunks, what we do is we can select different embedding models like OpenAI's embedding models, or sentence transformers, or Mistral's embeddings. And you can take each chunk, run them through this model, and you will get a vector representation of their meaning. Now, this is stored. So along with the chunk and its corresponding embedding, they are stored in the vector databases. We have different kinds of vector databases like Pinecone, Chroma, and FAIS is a temporary storage mechanism which stays in your RAM. Now we have these embeddings in our storing. Now let's go to the next step, where you receive a query, and that query's embedding is calculated using the same model, and which again in turn uses the same method, and you finally get the query embedding vector. Each of these chunk embeddings is compared with the query embedding, and their cosine similarity is calculated, and based on the similarity, the top k chunks are retrieved. Let's say k is 3. And so we take the top 3 most similar chunks. And then, along with the prompt given by the user, you also provide these 3 chunks that you have selected in this previous step as context to the AI, and then you can finally generate your response, which will be more grounded and more context aware than just sending the prompt to the AI model. So in order to solidify this concept of RAG, I will tell you a story from my personal experience during my master's in Germany. I had to write a thesis report on a completely new concept called diachronic word embeddings. Now, there was not much information available online, and the reference material book was in German. And the book was 1,000 pages long with 75 chapters, and the topic of my interest was scattered throughout the entire book on various pages. Now, it was impossible for me to go through the entire book to make my report. So whenever I thought I had something useful, I made a note of the page numbers, translated those paragraphs into English, and then I saved those translated parts in my Google Doc. So when I was writing my final report, the questions whichever I had in German, I translated them into English. And then I searched for a relevant answer to these questions in my already translated Google Doc. And then I've used these passages to complete my report. Now I would like to ask you to pause the video and ask you to map the tasks that are involved in the RAG process with all the tasks that I have done in my story. If you see, this is the answer. So me breaking down that 1,000 pages book was the chunking process. And the translation that I did into English was the embedding. I saved it all in a Google Doc, which was the storage. Now, translating the topics or questions again into English is converting the query into an embedding. And retrieval is looking for a relevant answer in that Google Doc. And finally, writing my thesis response was the augmented response generation. I hope the story helps you to remember the concepts and the steps involved in RAG better. Now, let's walk through a quick demo of how this RAG-enhanced synthetic data generation actually works. So if you see, the document here is the ICMR Guidelines, one of the most comprehensive references for medical trial regulations in India. In this section, you will notice that the material directly is relevant to our use case. And if you see in clinical trials that include women of reproductive age, there may be occasional pregnancy, and in such instance, the woman should be withdrawn from the study. So this is a specific guideline that is unique to these ICMR guidelines. And including this context will be helpful in generating proper synthetic data that is more relevant to the context. Now, I will show you a comparison of outputs generated with and without context, so you can see the difference immediately. So here I'm trying to generate some female patient profiles in this clinical trial for a contraceptive drug. And here I can go down and mention all the relevant column names, and then click on Go Now. So the data loading has completed, and if you see, these entries are mostly homogeneous, and it just says all not pregnant and different kinds of scenarios. But it gives trial eligibility as eligible for everything. But this data is okay, but it is not diverse enough, and it doesn't cover all the scenarios. So what we can now do is we can add some context to this by uploading a PDF file that we've just seen with all those regulations and guidelines. So if you see, I have uploaded the ICMR National Ethical Guidelines here. And then now maybe let's regenerate these trials and see how they look. So now we have some data that has taken context into consideration, and now we have more diverse data where if a patient becomes pregnant in between, they are immediately terminated from the analysis, and their status is monitored. So this is one of the example of how RAG can be used to generate synthetic data, and that synthetic data again is further used for fine-tuning and evaluating your AI models. So these kind of synthetic participant profiles, they can be used to train smaller classification models and also run controlled simulations of various trial scenarios like the ones we've seen now, and also design edge case evaluation. So a common question is, why not just rely on RAG instead of fine-tuning? I've already published a detailed video explaining when fine-tuning becomes essential. Maybe you can check the link above. And this feature of allowing you to upload PDFs and helping you to convert those PDFs into relational data, this feature is currently in beta and it will be available soon. So maybe share your thoughts in the comments. I'd love to know whether this capability would be useful in your workflow. Thanks for watching.